So, welcome back students. Last class basically we are discussing the chiral pull approach, and we said that we will be trying to complete the stereochemical strategies, and hopefully today we will be able to do it. We will be just discussing the chiral pull approach, and then we will give you one example where you start with the achiral compounds and how to bring or how to create new stereocenters on that one. Now, this particular problem which I am now going to pick up, it basically involves a kind of divergency, but divergency is basically generated from the starting material, not with the reagent based divergency. This particular compound is a very good building block, its name is Garner aldehyde. Now, Garner aldehyde, both the enantiomers you can prepare and you can use those as a very good synthetic intermediate. Now, I have drawn both the enantiomers of Garner aldehyde. I said this is plus, this is minus. In reality, I do not know what exactly this is, but this is plus and this is minus, just a assumption. And I am saying that this Garner aldehyde can be prepared from amino acid as a chiral pull. First, if you try to correlate, probably you can figure it out, this Garner aldehyde can be easily made from a simple amino acid which is nothing but a L-serine. Because you said L amino acids are plentifully available in the nature, these are very cheap, easily commercially available material. Now, first we will be using a reagent which is often used for amino acid or amine protecting agent, it is called Bock anhydride. Now, Bock anhydride poly you can see its structure. Bock anhydride was usually used for amine protecting group, and a mild base like potassium carbonate was used. So, initially if you use this one, you get this NH Bock and CO2H, fine. Now, this as a acetonide protection is there in the target molecule. So, it was simply treated with 2,2-DMP or 2,2-dimethoxypropane to basically protect the alcohol and the amine group as its acetonide. The Bock remains same, and then you are having this CO2H. Now, eventually if you use potassium carbonate and methyl iodide here, it will basically convert this carboxylic acid to carboxy methyl ester, this is also required. Now, simple thing is you do a selective reduction with dibal which can reduce to ester to its corresponding aldehyde, which is very well known in the literature. So, what exactly you are now having? You are having one enantiomer of this Garner aldehyde can easily be prepared starting from L-serine. Now, my next question is, for synthesizing the other enantiomer, in principle you need D-serine where the stereocenter has been inverted, but I am saying that D-serine is extremely costly, D-serine is very costly. So, can you use a similar kind of L amino acid, because L amino acids are very cheap in nature? My answer will be yes, you can definitely do it, but if you know the structure of the amino acid in true sense. I am now trying to draw the structure of another amino acid which also belongs to the L family. The amino acid which I am now drawing is named as L-methionine, is also L amino acids naturally occurring, so it is very cheap. Now, L-methionine and L-serine, now if you do the structural analysis, this is L-methionine. Okay. and this is your L-serine. Now, only difference is everything is similar, you are having extra SME group. Now, why this SME group is required, now I am basically discussing. So, first this L-methionine, you do the similar kind of reaction. First you protect with Bock anhydride. So, you get this part is there, your NH, Bock and your CO2H. Now, as we need to construct the enantiomer, if you try to now go back to your original divergence concept, I said that if you have a same starting material, you want to create divergency, you first pick up the left hand side, keeping the right hand side intact. In other operation, you first do the right hand side reaction and keeping the left hand side intact. So, you will try to follow the same principle. Now, here the carboxylic acid is there, which now will reduce with a boron THF, and this reduction will give you the primary alcohol here. Now, this primary alcohol will be now protected as acetonide with 2,2-DMP. So, 2,2-DMP same way in Bock and these things. Now, in earlier case L-serine already having a hydroxy group at the left hand side. Now, here the hydroxy group we are creating at the right hand side to close the ring. Now, only thing you need to now convert to this group to a aldehyde. Now, there are 2 carbons, you basically need 1 carbon, means that somehow down the line you need to keep 1 carbon extra. Now, here what I do, I will oxidize the sulfur with oxidizing agent sodium periodate to convert this sulfur to a highest oxidation state of sulfur to a sulfoxide. In Bock. Now, sulfoxides are very strong electron withdrawing group, and this kind of sulfoxide elimination also available in the literature, probably similar kind of reaction we explained when you talk about selenium oxide seal elimination. Now, this is also similar kind of reaction, it basically goes through a 2,3 sigmatropic rearrangement and then basically give you a simple elimination. So, you now create a double bond here. Now, this double bond definitely you can easily chop through a ozonolysis or oxidative cleavage. If you do this ozonolysis, you will basically get CHO at this end. Okay, we will write it in the separate page to have a better view. So, you have a compound like this in Bock. Now, what we do? We just do a ozonolysis. So, basically having this compound in Bock. So, this is nothing the enantiomer of the Garner aldehyde. So, some same starting material or similar kind of chiral sense. So, you have now are saying that L-serine gives you plus enantiomer and L-methionine gives you the minus enantiomer. So, the basically the divergency is coming from the starting material structure, though the absolute absolute configuration on the stereogenic center remains same. The starting material serine is having this structure, the starting material methionine having this structure. So, what we do? We first, in the case of serine, we do the acetonide protection at this stage. Now, in case of methionine, we convert this CO2H to CH2OH, do this acetonide protection here. So, this is your left hand side reaction, this is right hand side reaction. So, that is why you basically created the handedness in the final product. Now, handedness is basically nothing but your creation of two different enantiomers, but also you need to be very careful about the FGI, which will eliminate the SME group in form of sulfoxide, then you do ozonolysis. So, this kind of divergence is quite possible if you do a close analysis of the starting material structure. In the final part of this absolute asymmetric synthesis, we will talk about if you having a achiral substrates. Achiral substrates, what is the usual way to create chiral substrates or to create asymmetric center. There are numerous ways. The very earlier approaches of still is very popular is chiral auxiliary based approaches, and the other things are basically you react with chiral reagent or chiral catalyst. This is the two principal ways you can start with a achiral substrates and synthesize a chiral substrate. Now, we will try to focus it out only the chiral auxiliaries, because we do not have enough time, and for people who want to put more emphasis on this one can attend a basically advanced course on asymmetric synthesis. So, chiral auxiliary I will try to give you a schematic view. If you have a substrate which I am saying is achiral. Now, first this substrate was you attach a auxiliary or a basically use kind of a you basically do a derivatization with the help of CDA, is basically extension of a CDA technique through a covalent attachment. Covalent attachment. Now, this CDA having a stereochemical center or stereo center. Now, due to presence of the stereo center, now your new substrate is basically having substrate as well as auxiliary. Now, this is basically chiral. Now, you do the necessary FGI. Now, this FGI will be doing it on the substrate part. Now, the auxiliary part having a stereo center, this stereo center will basically control the formation of the new stereo center. So, now we will see that your substrate will be having some new bond formation, and then the auxiliary remains here, and now you get rid of the auxiliary. So, basically now we will be getting your substrate as a new bond. So, this is now substrate becomes chiral. So, starting from a achiral substrate, you can basically end up with a chiral substrate is nothing but a extension of a chiral derivatization agent. So, these things we called a auxiliary. Now, auxiliary similar like your if you have a CDA, we said the auxiliary have certain prerequisite. What are the prerequisite to be a good auxiliary? Prerequisite of a good chiral auxiliary. The prerequisites are this must be cheap and or commercially available, or you can even make it in the lab, but it should be cheap. Okay. The second point is very important, it must be enantiomerically pure, means this should be available in single enantiomeric form, must be enantiomerically pure. The covalent attachment by which you can basically attach the substrate to the auxiliary, the covalent attachment must be complete, means the reaction should undergo completion, covalent attachment must go to completion. This is one of the essential criteria. And finally, the auxiliary must be chemically inert under the reaction condition, chemically inert under the FGI condition, under FGI, and then the auxiliary can be easily removed, and if necessary can be reused. So, these are the main 5 criteria which we also discussed about the CDA. Your auxiliary should fulfill this certain criteria. Now, next we will be taking a example and we will try to formulate how this auxiliary is helping. We say we will be trying to synthesize this compound. The starting material is given to you. Starting material what I am giving? This ester. So, ethyl propionate I am giving to you starting material. So, it is a achiral compound. So, what basically you need to do? You need to put a carbon carbon bond here in stereo control fashion. So, now your entire thing is probably will be, now I am doing the retro. I am saying that now if you take the starting material and if you can fuse it with a chiral auxiliary, this auxiliary is there. Now, this auxiliary is there, but the initial starting material having a carbonyl functionality. So, enolate chemistry can be used. Now, if I treat with a base, this compound will basically give you a enolate O metal and auxiliary remains here. Now, if you react with a electrophile, this electrophile will now try to attack to this sp2 trigonal carbon, which is basically flat at these things. It can attack from this top face or bottom face, which could be Re or Psi depending on the CIP nomenclature. Now, I am saying that this auxiliary has its own chiral bias. So, auxiliary will now dictate from which face the incoming electrophile is approaching. So, now what auxiliaries are people mainly using? There are many auxiliaries reported in the literature. I will try to pick up one auxiliaries which is very often used, named as Evans oxazolidinone. The Evans oxazolidinone having this kind of structure, Evans oxazolidinone. Now, as I said, these oxazolidinones are commercially available, or even you can make it in the lab. These oxazolidinones are best prepared starting from this corresponding amino alcohol. You react this amino alcohol with diethyl carbonate or other reagents, you can basically remove 2 equivalent of ethanol by simply heating to get this oxazolidinone. This amino alcohol you can simply get it from the corresponding amino acid. Okay. Now, once the oxazolidinone was done, this R group should be little bit bulky. So, normally you prefer isopropyl, means the valine is amino acid, or PHCH2, which is phenylalanine, usually preferred. These compounds are commercially available. So, now how do you do the synthesis? Let us first make this oxazolidinone. So, first we take this valine. Valine carboxylic acid group first need to be reduced. So, do a boron reduction, you basically get the corresponding amino alcohol. As I said, react with the diethyl carbonate, heat it, 2 equivalent of ethanol will be releasing, and you get this as this oxazolidinone. The oxazolidinone is a cyclic structure, and the covalent attachment will be now possible through this amide nitrogen. So, now your compound is having basically, I have given you a propionate. This propionate you can easily convert it to corresponding propionyl chloride. Now, chloride and amine can easily be coupled. So, once you couple this chloride and amine in presence of a base, you can basically get this CO, N, CO, O, these things. Now, oxazolidinone, the structure has been very judiciously chosen. It also fulfills certain other criteria. Now, what I do? You treat with a base like LDA to abstract the hydrogen, one of the hydrogen, to generate the enolate. So, you will be now generating the enolate. You have this O Li. Now, this oxazolidinone seems to be in a cyclic chelated form with this OLI. This OLI basically makes this rigid chelate. So, this rigid chelate is very important. Now, you can also think about having a possibility of another enolate, in principle like this. So, one is basically Z, this is oxygen hydroxide, this is Z enolate, and this is E enolate, O Li thing. Now, I am saying that normally Z enolate basically forms in a predominant fashion, because in case of E enolate you have a severe allylic 1,3 strain. Allylic 1,3 strain, if you are familiar, you can understand. So, allylic 1,3 strain basically makes your Z enolate more predominant or major enolate. Now, you have this Z enolate in this reaction mixture, N C double bond O, lithium. Now, you react with allyl bromide as your electrophile. Now, see that this isopropyl group in this oxazolidinone blocks this bottom phase. So, or the alpha phase was basically blocked by this bulky isopropyl group, and that was very important. So, then your incoming electrophile only will get the beta phase approach. Eventually, this explanation will be quite clear if you use a simple ball and stick model. So, beta phase approach is now favored, and then finally, if you now react these things, okay, you get this compound. Now, as I said, the next prerequisite is your auxiliary removal. So, auxiliary removal can be done by numerous ways. The best way, you can do a reductive cleavage. You can do a reductive cleavage. Reductive cleavage means you treat with dibal, you can basically get the corresponding alcohol. You can treat with same dibal or lithium borohydride, you can get this compound. There are also other ways you can cleave it. I am just giving you another approach. You can treat this compound with this our old friend oenrabamine. Once you treat this compound with this oenrabamine, that will cleave to give you this oenrabamide. Now, this oenrabamide give you much more flexibility. You can basically now convert this oenrabamide to react with some other nucleophile, so that if you in your synthetic exercises, if you need to put some other functional group. So, we are basically discussing how this oxazolidinone can be cleaved in a efficient way. We say the reductive cleavage is very well known, dibal or other things can easily be done, that will basically give you our target molecule, that is fine. Now, I said you can basically cleave it with the oenrabamine like MENHOME, HCl salt, and then this cleavage will basically undergoing, this will basically undergo a transamidation kind of reaction, and it will give you NMe. What is this? Your oenrabamide. Now, this oenrabamide basically react with any simple nucleophile, so that if your final target now has to be a this kind of compound. So, this kind of nucleophile could be your vinyl Grignard, could be your acetylenite Grignard, and based on this you can basically get compounds like this kind of vinylic ketone or this kind of propagylic ketone based on your desired requirement. Now, the stereocenter, which is our main target, can be fixed very efficiently with the help of Evans oxazolidinone methods. Now, similar kind of auxiliaries are very well known in the literature, we are not talking about, but I am just give you a couple of name. Evans oxazolidinone we have just discussed. There are reports which named as Myers ephedrine or pseudoephedrine based auxiliaries. Then Myers oxazoline, these are not same Myers, this is Myers, this is Myers, Myers oxazoline as well as bicyclic lactam. Now, we are not talking about these auxiliaries due to time constraint, and this is beyond of our scope. We also have Opolzer's saltam. So, there are many auxiliaries which are reported in the literature. There are auxiliaries named as Williams oxagenone. These are the auxiliaries which probably you need to find it out in the literature. There are Seebeck auxiliaries. So, all the auxiliaries basically working in the similar kind of principle. You need to have a covalent attachment first, and then you do the FGI, then you remove the auxiliaries. The auxiliaries all having a inbuilt chiralities. So, our stereochemical strategies ends here. Next lecture we will try to figure it out. Probably we will take a medium sized complex molecule, it is a natural product. Till now what are the strategical disconnection we have talked about, we will try to apply those knowledges, and then we will see how a real problem can be tackled. We will take a real example of a natural product, though in the study of this course we have talked about few natural products. Now, we take a real natural product, we will try to analyze through the knowledges which we have acquired during our discussion. So, have a good time and see you in the next lecture.